Let's put this in practice in the context of a handful of selected candidate materials. We go from to common construction materials for columns: wooden, granite or concrete, and cast iron, structural steels, or an aluminum. Right? They all represent range of density values from 700 kilograms per meter cube for wood, the spruce wood, all the way up to 7850 for a structural steel. Costs also vary considerably. The aluminum is most expensive. The, the concrete, poured concrete, is the cheapest. Modulus varies by quite a bit, and the compressive strength varies by quite a bit as well, as you can see. Right? So depending upon the first situation where F is 0.1, H is 3, we get to evaluate what is C1 and C2 based on these two equations. The best way to solve this problem is to be able to set this up on an Excel spreadsheet and then set up additional columns for C1 and C2, and then for different values of F and H, create another additional set of columns. Go ahead and do that, and this is what you will get. You can compare what you find out with what you're talking about right now. So in the first case, you will get a material index for based on the first constraint by this range, and the second constraint by this range. We'll come to that column in a bit, but C1 and C2 are calculated based on these two constraints. Okay, so using this equation, you'll get 4.2 as an overall cost. Okay, for this combination of F and H. And the overall cost based on this material index for the value of F and H based on the second constraint, the buckling constraint, is in the second column. If you had only one constraint to consider, you would select the smallest value, if only the first constraint to consider, and the cheapest material would be brick in this case. If you only had to look at the buckling constraint as opposed to the compressive load constraint, the cheapest system would be the poured concrete. In this situation, for this design, we want the material to not only at the minimum satisfy the compressive constraint, but also the buckling constraint. So we have to basically choose for any given material which of the constraints are dominant. Right? If you go cheaper than here for spruce, it will not satisfy the second constraint. So the controlling cost is a Cmax, which is $11.24. So in each case, you will see that the second column, right, is the controlling constraint. And so the greater of these two will get used typically, except in the case of poured concrete. Once you've found out what is the cost that satisfies both constraints, among them you choose the cheapest cost that satisfies both constraints, and you'll come up with poured concrete as the solution. Dwell on this implication. This kind of an approach is called a min-max problem, right? You use the maximum of these two constraints so that both the constraints are satisfied for cost. And then among all the different candidates, you choose the minimum. Okay. Why are we doing that? Take some time to clarify that in your mind. In the second situation, for larger values of F by H square, the coupling constant, proportionality. Right? You find out that C1 will give you all these values, and actually in this particular set of cases, C1 is actually the cost based on the first constraint is greater than for the second constraint, which is a different trend from what you saw earlier. Right? Using the min-max principle, right? You use the larger of the cost that will satisfy both the constraints, compressive load and buckling for each material, and then you choose the cheapest material that satisfies both constraints. Right? Again, based on the fact that you know Cm rho by sigma c based on the first table that we saw 2 slides ago, and Cm rho by square root of the modulus E. And then for this value of F is 10 meganewtons and H 2 meters, we substitute that for each of these cases, and we come up with the situation over here, and we say that for a combination of F and H, where F by H square is larger than in the first case when F was 0.1 meganewton and H was 3 meters, right, the selection changes from concrete to cast iron. Right? And that's what we've seen graphically. Right? What we have done through the Excel spreadsheet calculations has satisfied ourselves as to why that for the material that lies to the lowest left region for any given coupling constant line of slope 1 and a given value of F by H square as an intercept, what happens, right, when we choose the bottommost point on the left? Right? Bottommost point on the left in the first set of criteria was cast iron, low F by H square, concrete, low F by H square, and in the second case it was cast iron for a higher value of F by H square. Yes, you can sit and do these calculations for these 7, but what if you had to choose from a material universe of 10,000 or more? Right? That is where the power of the EduPack software comes into hand, because without actually doing these calculations one by one, you can graphically look at that and pick out the most suitable materials and then learn a little bit more about whether they can be processed in a particular way. There are other environmental concerns or handling concerns to look at, and also where you can procure them from. So that's the advantage as a design engineer when you begin to use the EduPack platform that was recently acquired by ANSYS Grantor. So that was a case where we plotted 2 property indices on a log-log scale and use a coupling line to take into account different designs based on variations in load, variations in dimension, and variations in material attributes. Alternatively, you can use a penalty function z, where if you are to look at a combination of mass versus cost, right, where you want to minimize cost and you want to minimize mass. Right? How do you go about doing that? This will be a concept for a later date.